Hey everybody, this is Mr. Schultz here with you, and we're going to take a look at 611, but this time we're going to be taking a look at day 2 of this. So we're going to be looking at the same section, but a couple of different problems. Again, we're going to be representing exponential growth. So far in this course, you have been investigating the family of linear functions using multiple representations, especially tables, graphs, and equations or rules. In this chapter, you will learn about a new family of functions called exponential functions and the type of growth that it models. So thinking to yesterday and talking about Lenny and George and their rabbit farm, question 6-3 kind of builds on that. So it says this: Lenny and George want to raise as many rabbits as possible, so they have a few options to consider. They start with a larger number. They could start with a larger number of rabbits, or they could raise a breed of rabbits that reproduces faster. How do you think each of these options would change the pattern of growth you observed in problem 6.1, and which situation will yield the largest rabbit population after 1 year? So they give us 3 cases here. Let's take a look at these cases. Okay, so in 6.3, I'm calling these case 2, 3, and 4 because case 1 was our 6.1 from yesterday, where they started with 2 rabbits, and each of those two, and in each pair of rabbits had 2 babies. So in 6.3 it says this: to help answer these questions, model each case below with a table for the first 5 months. So in each of these 3 cases, case 2, case 3, and case 4, I want you to make a table that represents 5 months. So take a second, see if you can build those tables, and then we'll take a look at it in just a second. So this would be a great time to pause the video and try to build a table for the first 5 months for each of these 3 cases. Alright, so I started off by making the 3 different tables here. Let's read case 2 here. It says that they would start with 10 rabbits, and then each pair has 2 babies per month. So if there's 10 total rabbits, then there'd be 5 pairs, and each pair has 2 babies. So if there are 5 pairs and each pair has 2 babies, well, that'd be a total of 10. So there'd be 10 babies, including the 10 original rabbits. So you have a total of 20 total rabbits then. Same type of thing here now. So to get to the month 2, you are starting with 20 rabbits. That makes 10 pairs. Each pair has 2 babies. That makes 20. So 20 plus the original 20 gives you 40. And maybe you can start to see this pattern. If you can't, that's okay. So 20 pairs times by 2 would be 40, and 40 plus 40 is 80. Hopefully now you can start to see this pattern that it is doubling. Let's take a look at case 3. So this is our kind of middle case here. Case 3, start with 2 rabbits, and each pair has 4 babies per month. So let's start to think about this now. So if there are 2 rabbits and each pair, that means that there'd be 1 pair and it has 4 babies. So that'd be a total of 4 babies plus the original 2 rabbits would be 6 total rabbits. Then in month 2, you would have 3 pairs from those 6 rabbits. So 3 pairs times by 4 babies would be 12. So then 12 plus 6 would be 18. So then 18, you would have 9 pairs times by 4 babies per pair. So then you would have 9 times by 4, which is 36. But I've got this 36 plus this original 18. Our math is starting to get a little bit harder, so feel free to use a calculator. But you should be up to 54 rabbits there. So then 54 rabbits divided by 2, because we're looking for pairs, would be, about 27 times by 4. So 27 times by 4, that'd be equal to 108 rabbits now, plus that original 54 should be 162. Now we could keep going with this pattern, but let's see if we find a pattern here. Well, I see from 2 to 6 it's increasing by 4, then this is going up by more than 4, so it doesn't seem like it's adding. Maybe it's doing that same multiplying that we saw here. It's definitely multiplying by 2, but you'd multiply by 3. You would multiply by 3. You would multiply by 3, multiply by 3. So this seems to be multiplying by 3. So 162 rabbits times by 3, you should get 486 rabbits here, which I'm going to do this in blue here so that it matches. 486 rabbits. Okay, let's see our last case here. So our last case says this. Starts with 2 rabbits again, but each pair has 6 babies per month. Okay, so if I have 1 pair of rabbits times by 6 babies per month, well, that'd be 6, and 6 plus 2 would be 8. So then I've got 8 total rabbits, which makes 4 pairs of rabbits times by 6. 6 times 4 is 24. Plus I've got the original 8. This should be going up to 32. Now maybe from this and from seeing it in the previous 2, you can kind of guess what is going on here. This is multiplying by 4. Multiplying by 4. So 32 times by 4 would be 100. Let me get that back into purple. Would be 128. Times by 4 would be 512. Times by 4 would be 2,048 rabbits. Okay, so we've got our table for the first 5 months, and it says this. Which case will give Lenny and George the most rabbits after 1 year? Well, I'm going to take a guess that it's this case 4, because it seems to be growing way faster than the other cases. So case 4 seems to give you the most amount of rabbits. How many rabbits would they have in that case? Well, I would just have to keep multiplying by 4 and keep track of where I'm at. So let's see what this looks like. So instead of having you watch me click times 4 and then write a number down, I just went through and did all this. So times by 4, times by 4, times by 4. Oh my goodness. All the way down here, you get 33 million rabbits. So 33,554,432 rabbits in case number 4. Now, obviously, this is not really true because there's no way that somebody would go from 2 rabbits to 33 million rabbits in a year, or closer to 34 million rabbits. But you got to see what this exponential growth does. It really makes things grow really, really, really fast. So yeah, let's see what the next problem looks like. So in problem 6-4, it says this. Look back at the tables you created, and then it says, what patterns do they all have in common? So the thing that we found that was happening was there was some sort of multiplier. Our first one was times by 2, next one was times by 3, next one was times by 4. They were all multiplying. Multiplying is our big takeaway there. Let me write that a little bit cleaner here. Multiplying. And so when you're multiplying, this is what's called an exponential function, meaning that it's so if you hear somebody say something like it's growing exponentially, what they mean is that it's growing by multiplying, not by adding or subtracting. So for part B, it says this. Obtain the resource page and graph the data for case 2. We're going to use the Desmos tool here. We're going to graph the data for case 2 and then write a complete description of the graph in part D. So let's take a look at that on the next page here. Okay, so on our tool here, on the left side, I just kind of scrolled down and then input the first 5 months worth of data there, and then I just kept going. Remember, this is just a multiplier by 2. So our exponential graph looks something like this. It basically starts off, and it kind of goes slowly. Then all of a sudden, it just kind of explodes up. This is something that you maybe have seen a bunch of with some of the coronavirus stuff. The viruses are usually modeled by some sort of exponential graph, which is why people were very concerned about it, because it starts off and it looks like it's going slow, then all of a sudden one day it just starts to make these big jumps and explode up. So this is what that graph looks like. Let's take a look at some of the questions that are associated with that on the next slide. So our first question says this on 6.4 part C. Answer the questions about these graphs if you have not already done so. What is the domain and range of the graph? Well, domain is just basically looking for what is the x values that exist in the graph. The range is what are the y values that exist. The y values that exist. So the domain would be that you're talking about x basically goes from 0, and then it can just keep going on and on and on. It goes all the way to infinity, which that sideways 8 means infinity. So it'd be 0 to infinity months. In theory, they could just keep this going on and on and on and on and on, and keep on growing in theory. Of course, in practice, most likely not, because they wouldn't have a space that would be big enough. But then the range, well, we started at 10 rabbits. Then same thing, we just absolutely exploded in growth there, so it could go all the way up to infinity. So our next question says this: is it continuous? Meaning, are the points connected or is it discrete? Are the points not connected? In this one, we've got a discrete graph, and the reason why they're not connected is because if they were connected, then in theory, you'd be able to have something like 10.5 rabbits. Well, that doesn't make any sense to have half of a rabbit. I mean, I guess if it's partially born or if it's partially growing or something like that, but it doesn't really make sense. So this is a discrete graph, meaning that it's got that the points are not connected. The very last thing is it a function? In this case, this may not be a vocab word that you've heard much about, but basically a function is this: is there one x value that produces only one y value? So in this case, yes, it is a function because there's only one x value that produces only one y value. The kind of test for doing something like this is called the vertical line test. And basically it means this: if you can draw a vertical line anywhere on the graph and it only touches one point, then it passes the vertical line test, which makes it a function. So in our case, even though it's going really, really steeply up, in theory, if you draw a line straight up and down, even on this almost straight up and down line part, it is only going to touch at one point. Even though it looks like it's really close and might be touching on other points, it is only going to create 1 point of data there. So that is a whole bunch of everything for today. So have a great rest of your day.